beginning, we are ready to start. So the first lecture all morning is given by Matthias Kovatsch. Matthias is an Internet of Things researcher at ETH Zurich, Switzerland, with a focus on web technology for highly resource-constrained devices. He is active in the Internet Engineering Task Force, IETF, the IoT Industry Working Group by the Eclipse Foundation, and the Contiki Operating System Community. In 2011, he was also visiting researcher at SICS Swedish ICT in Kista, Sweden. His background is rooted into electrical engineering and computer science through an interdisciplinary study course. He received the academic degree Diploma Engineer, equivalent to a Master of Science, from the University of Erlangen-Nuremberg, Germany, in November 2008. During his studies, he was working with Siemens Pte Ltd Singapore and the Fraunhofer Institute for Integrated Circuits, IIS. The latter, he also conducted his diploma thesis developing the ZigBee-based application framework for medical wireless sensor networks. Since March 2009, he is at ETH Zurich, Switzerland, and a Ph.D. candidate in the Distributed Systems Group at the Institute for Pervasive Computing. Thank you very much, Matthias.
Thank you very much for the introduction. So I hope everyone is ready now. We had some technical issues here, so I hope the slides are online in the cloud, but the internet is a bit shaky, so cross fingers and hope for the best. The idea behind this, you can follow the slides during my talk, so they are here. You could scan the barcode or go to this URI and have them there as well if there's something like the font too small or whatever. So in the style of yesterday afternoon, we will keep it very technical today. So I'll give you an introduction to CoAP. We will look into some details, so really how does the encoding work, what are the mechanisms in there, why we have them in there, the general pictures, so a step back, and so CoAP is a web protocol, so it's built on the REST architectural style. So, but what does it mean? So how do you use REST to build Internet of Things applications? So we will revisit that, and then you get some getting started to know what libraries are out there, what you can use. And in the afternoon, we will have some hands-on where you actually start implementing CoAP servers, clients, and so on. And to prepare you for the hackathon on Saturday. So I hope enough people have copied this address and can propagate it. So I think we had a lengthy introduction already, so let's skip this. That's the agenda. I just told you about it. So first, the Web of Things. So we're always talking about the Internet of Things. What's the Web of Things? Constraint application protocol CoAP, building RESTful IoT applications, and then get you started with some libraries and code to actually do it. So what's the Web of Things? Basically, it's what the web is for the Internet. So it's supposed to be the application layer for the IoT. So the good part is the web is basically the de facto application layer for the Internet. So most of our services, of our applications, they run on the web. So there are other applications layer like email or FTP, but the most successful one is definitely the web. So the advantage we have there, so the well-known patterns, how to design applications, the integration of cloud services, so for scalability and so on, and this nice thing about web mashups, so to easily connect different applications together to build something even better. That's what we want to have for the Internet of Things as well. And that's why we in our group and at several other places, we follow this idea of the Web of Things to make the Internet of Things even better, to have a nice application layer for it, and really connect everything together. And there are basically two reasons. One is interoperability at the application layer and usability. So the nice thing is, if you start from the web, or the basic idea started actually with HTTP. So you have HTTP libraries for basically all the devices out there. So for all the platforms, from really small microcontroller-based devices to big Java systems, let's say. You have the libraries, and if you look out here, I already said most of our services, so digital services that we use to enhance our everyday life, it's HTTP-based, so they can all talk to each other and they understand the application layer protocol. So interoperability, that's the one big point. And the other one is usability. So we have all these basically design patterns, how to create web applications. They are very good. I mean, the web is super scalable. And a lot of developers know how to create code and applications for that. And the nice part I already mentioned, you can do these mashups that's based on lightweight scripting to do that. And yeah, scripting really increases productivity. So you get results fast, you can really sketch applications quickly and then do rapid prototyping and then get something really nice very quickly. So basically kids can already program web applications. I mean, there's so many small companies, they still go to school, but do, I don't know, the back end for some medium-sized companies and so on. And yeah, the point is the web fosters this innovation, so we want to have the same creativity and innovation for the Internet of Things as well. So that's why we should go the Web of Things way. However, this idea is very nice, that there was kind of an obstacle. So a major part of the Internet of Things will be made up from resource-constrained devices. So Carsten already gave you an overview what that means, resource constraint. So we are talking about this class 1, so about 100 kilobytes of flash and only 10 kilobytes of RAM. And yeah, for that, you also need low power networks because the energy is also constrained. You want to run on battery. And if you, I don't know, have 50 billion devices out there and they all need 1 watt to run, then we won't say, for instance, the energy problem with the Internet of Things, we will cause it. So, yeah, we want these devices to be cheap. So for the communication part that makes it an Internet of Things device, we actually want to go maybe something like $1. Because if you want to buy a light bulb that has the IP address and the communication, you cannot add $40 just to connect it to the internet. At the moment, you can do this because it's really fun, so you get these Philips lights or whatsoever. It's good, but if this should really kick off and you get billions of devices, it must really cheap you to enhance them with this smartness. And what we learned mainly from wireless sensor networks, that TCP and HTTP is not a good fit for these low power networks. So you have small frame sizes, they are lossy, so you lose a lot of packets and so on. So we have a problem running this directly on the devices. There are some projects also in Contiki to use HTTP, but for those who use it already, if you want to get, for instance, the index side of the border router, which is HTTP, it already takes several seconds to get 3 lines of text. So that's not really what you want to have if you want to control something. You want to have instant feedback and so on. So there must be a better way. And that's basically where the constrained application protocol comes in. So this whole problem was also recognized by the IETF, the Internet Engineering Task Force. So basically those guys who standardized HTTP before, did the design with HTTP 1.1, this RESTful approach. And they saw that there is this gap, and this gap is now basically closed by the constrained application protocol. And today is all about this protocol, and I'll tell you some more of the details right now. So it's a protocol based on REST, but we designed it from scratch. So we didn't take HTTP and stretch out some parts and glue something here. It's really, we looked at, okay, what's the REST architectural style? And what's the core of it, and then we started to design a protocol with these guidelines and constraints, and then created the new protocol. The nice thing, because it's still REST, there's a transparent mapping to HTTP. So Carsten introduced that, so there's get, post, put, delete. We also have that in HTTP, so it's very easy to have something in the middle that translates, but translates in a very transparent way, so this translator doesn't need to know the application. It just can directly connect these 2 protocols. That's very nice to integrate new services based on CoAP into the existing web. And then the thing, we also have actually additional features in CoAP that make it a better fit for the Internet of Things. So with HTTP, eventing is always a problem, or to get push notifications. So there are so many ways to do it. Most of them are quite heavyweight, so that's not going to work in low power networks. So yeah, this is also tackled by the CoAP. Let's call it CoAP from now on. It's shorter. So how does it look like? So it runs over UDP. That's one of the big changes. No TCP. There is DTLAS, so the transport layer security for datagrams to have security. And then actually we have the option to use many other protocols as well. On top of that, that's CoAP. And you basically have two sublayers. So because it's UDP, you don't have any reliability. There's a small control layer that provides you or gives you this reliability back. So you get deduplication, so that you don't execute requests twice. And if your application needs it, usually you need it. You also have reliable transport, so you have retransmissions and so on. And then there's the request response sublayer, and that helps you with the RESTful interaction. So that's where get, post, put, delete, the options and using URIs and so on is implemented. So how does it look like? So I have to use this right. The smallest message you send over CoAP, it's just 4 bytes. You have this base header, it's the orange box on the top. So you have the classic information you need in the protocol. So there's a version that you can do updates later if you really need to fix something that went wrong. We have the type that basically says, helps you for this control layer. So we need something like you send something, you get an acknowledgement. So this is the message type. There's something like a token, and you need to encode the token length there. I'll come to this in a sec. There's a code that basically gives you what method is it, or what response code is it. And then we have an ID there that we need to implement this reliability. The whole thing is binary encoded, so it's much smaller than HTTP, for instance. And the encoding itself, there's a focus that the parsing complexity is very low. So you don't need to allocate a lot of buffers, and you can just do it on the fly and very easily get your values, and can do this easily on 8-bit architectures as well. So I was mentioning this token, so that's what comes next in the CoAP message. And it's basically a handle the client chooses to identify a specific exchange. The thing is, remember it's UDP, so there's no connection that we would have for HTTP with TCP. It's really we send something, and then at some other point we get something back, but there could be something going on in between. And therefore we need this token. And then we have options. So that's basically what header fields are for HTTP. So it's extensible. So we can provide new mechanisms to update the protocol, why it evolves and why it's in the field. Many of them are the ones you already know from HTTP, or most of you, at least I hope. So something like the location field, the max age, which is cache control, you need there. ETH is something of that. There's also content format, so what are you sending? So it's pretty similar to HTTP here as well. Then there's something, a marker, so this is how we encode it, and then you can have a payload as well. The point is, this marker only goes there if you actually have a payload. It's one of the details, but I think we can do this if we really go deep into the code this afternoon, maybe. So, this option. So there's actually one of the more complicated mechanisms in there, how these options are encoded. We want to be small and low parsing complexity. So what we do, we don't have this ASCII encoded, no text encoded information. We have numbers that we assign to options. So there's an ID for each option. So you register them, and that's how you identify the different options. And there's this compact encoding. So it's a delta encoding, and there are two reasons. You can make it really small, and you can also enforce that the options, if you encode them, they are always in the right order. So there's no way you could mess this up and get somehow the wrong order. A reason for that, for instance, is the URI is encoded in options, and if you switch two segments of this path, you would end up with a different URI. You really want to make sure that options keep this order so you don't get any problems like this. Is this clear, what I'm talking about? If you have questions, if you're confused, just raise your hand, please, and ask and stop me. Okay, so we have this delta encoding. So what we have is basically 1 byte, and we use 4 bits for the delta, so that's kind of the offset to get to the option number, and then only 4 bits for the length. And yeah, 4 bits, that's really small, so we can't do large things. So actually, the longest thing we would get is something like, at the moment it's 12 bytes, so URI of 12 bytes, I mean if it's an integer or something encoded in 12 bytes, that's a lot. But we often need more, especially for this delta. So imagine the delta, you start with 0, then you receive a delta, which is, for instance, 5. Then you know, okay, I have to jump to 5, and 5 is now the option number. Then the next option comes and has a delta of 4. Then we have 9, and 9 is then the new option number. I'll have a short example shortly. But yeah, we want to be complex, so that's why we have these small bits. But we need to be extensible, so there are some options that have a number beyond 10,000. And if we only have 4 bits, then we really have a problem. So we can actually encode something. If the delta, for instance, is 13, we know that there will be an additional byte that we can use to encode higher numbers. And if we use the value 14, we know there will be 2 bytes following, so we have a 16-bit integer basically that we can add. And then we get ranges like here. So with 1 additional byte, we cover numbers between 13 and 268. And with 2 bytes, yeah, you can go up to 65,000. That's basically the limit. You also have for the length. UDP, for instance, has a theoretical limit of 65,000 bytes. So yeah, we could have that just one big option. Probably it's not useful, but there are no artificial limitations in the protocol. That's one of the main points. And yeah, after this header, then you have the value. So it's kind of this height, length, value encoding. You know the type because you have the number. The length is encoded, and then you get the value. There's even more encoded in there. So you have this option number, and there's metadata connected to it because you need it if you want to process this in a good way. So one of the most important things or concept in there is that they are critical options. So basically there are 2 types, the critical ones and the elective ones. Critical options, you really need to understand them, and if you don't know what this number stands for, because, I don't know, your implementation was very early and there came some new registry entries, you don't know what this is, then you have to return an error. You have to abort this because you don't know what the other side is talking about. The elective ones, they are really optional options, so it doesn't matter if you understand them, it would be nice, but you don't have to, then there's always a fallback, and you just reply to that. So that's very important to know that, and yeah, there's a good way to encode it. It's basically the least significant byte, so it's this, if it's an odd option number, we know it's critical. If it's an even option number, it's elective. But there are other things like whether it's unsafe for proxies to forward this thing. So in the web, you always have some intermediaries like caching proxies or local proxies for security and these kind of things. And probably you want to implement them once very efficiently, and then the rest can evolve. The application, you need new options and so on. You put it in there, but you can encode whether the proxy has to appear or not. So if you say it's unsafe to forward this proxy also has to return an error and tell the other parties that you cannot handle this. If it's not marked like this, it's safe to forward them, so he doesn't even know what's going on there. He just forwards this and everything will be fine. And then there's the last bit in there, the cache key. So these options often change what this request, for instance, means. And depending on what configuration of options you have a different response. And for caching, you know it from HTTP, you have to know to what kind of request this response you put in your cache belongs, so that you can hand out the right copy or the right response from your cache. And this is actually also encoded there, whether you need to consider what's the value of this in your cache key. So this is very flexible. It's again transparent, so you can have something in the middle that can stay there, but the endpoints, the application can evolve, and this still does work. That's the nice thing about it. And just to give you an impression, don't look at this at this. The first thing, you have this 1 byte option header. You have 4 bits, and we want to encode 11. That's the delta. So that 11 means we started at 0. Now we have option number 11. If you go back, you will see in the registry 11 is the URI path. So we know, okay, the option, it's about the URI. And then the length is 8. So we know, okay, there will be 8 bytes following to encode this. And then it's actually, byte string, UTF-8 encoded examples. 8 bytes and URI path. Okay, next option, we have another header. And the delta is 0. So 11 plus 0, we are still at URI path. It will be the same type of option. And the length is 7. And then 7 bytes here, postbox. So now we have encoded the URI in the CoAP message. Next header, 1 byte. Delta is 1. So we are at option number 12. 12 is it's the content format. And we have a length of 0 here. So there's actually no payload following. But we know that the content format is encoded as an unsigned integer. And implicitly, an unsigned integer of length 0 has the value of 0. So sometimes we can encode values without actually transmitting the values. So we can save 1 byte. Yay. Next option, we have a difference of 13. So we were at 12, so it's 25. Length will be 2. The thing is, 13. That's a special one. It tells us there will be 1 more byte to encode actually the thing. So we are at 25 plus 35. We are at 60. And 60, that's size 1. And we know, okay, 2 bytes will be following. And the value is 1000. That's the size 1 option. It tells us that the request has 1000 bytes. And that's basically how we encode it. You see, it's a bit more complicated than just writing it out in text, but the point was we want to make it small, and with these small encodings and lookups, that's very easy to implement on these small microcontrollers and these kind of systems. So, but what we want to do, we want to send messages and so on, and this is basically how this reliable transmissions work. So, you have a client and a server, and you send messages. And one of these messages is so-called confirmable. So you need to confirm it, and that gives you some kind of reliable transmission. So if the client sends this con message to the server, and it's somehow lost, it started a timeout. And after this initial timeout, it will just retransmit this message. So this timeout, it's a bit special. So it's a randomized value between 2 and 3 seconds. The reason is, imagine you have a classic sensor network, and you have a power outage, and they all go offline, then the power is restored, they boot up, and probably they have some logic encoded in there, and the first time they send everything really at nearly the same time. That will congest the network, there will be a lot of losses actually. And then to avoid this kind of synchronization, you have this random backup in there. So it's a random timeout, you have some kind of jitter, it's distributed over 1 second, and that gives you a better probability to actually get through. So let's assume the second one, it goes through, it's received by the server, and then what it has to do, if it's a con message, it has to send an acknowledgement. Of course, to stop the client from retransmitting, to acknowledge, yeah, I got this, that's fine. Problem is, we lose this again. Oh no! We will have another timeout if we don't hear from the other side, and have another retransmission. So, and the logic between here, it's a binary exponential backup. So that basically means you start with some initial timeout, and then you double it every time to give it some more time for the congestion to go away, and it also doubles this randomized value, so you get wide integer to distribute these requests that might have been started at the same time. So we transmit the second time, so it's the third transmission already, lost again, or no, the third one, and then we are finally successful. We get the acknowledgement, we know it's transmitted successful. So CoAP defines by default 4 retransmissions at maximum, so at most you will transmit something 5 times. And if you start with 1 to 3 seconds, double this each time, it can be 45 seconds until you finally transmit the last one. Sometimes this you don't need this actually, these retransmissions. Maybe your application is this simple, or you communicate that frequently that it doesn't matter that you lose something, and then you can use a non-confirmable, so non-message, and that's what I mean with this optional retransmission. So you can use this other message type because you know your link is pretty stable, for instance. There are almost no losses, or the application that is happy with less effort. Then you also have this other message type. So there are con messages in CoAP and non-messages. And what you pick defines what kind of reliability you get from the protocol. Okay, how does this map to requests and responses that we have on top and send through these messages? So this is how a request could look like. So we have this base header, these 4 bytes I introduced or showed you earlier. So we have version 1. We send a con type of message. And we have a token length of 4. So we know there will be 4 more bytes before the options start. And here in the code, we encode the get method, and then we give it the message ID. We have this token, so it's some opaque value, so you can choose something. The thing is, it's the client, so you can even encode something, what callback should be called if this thing comes back, or you can give it some more state that you need, so that you will get it back, and then you can decode some information there, but that's optional. And then you have some options. So important is you have some URI you're addressing, so hello/world. You pack this onto this con message, you send it, and what you can do with the responses, you can piggyback them directly on the acknowledgement. So we send the con request, we get the acknowledgement with a response, basically the same thing. Here's the type acknowledgement. The code is 205. If you remember, 200 codes from HTTP, that's successful, so that's okay. In CoAP, it's made a bit more explicit with this point class. So everything that has a 2, it means success, and 5 means there will be content. So it's not just okay, even there's something in the response. The important thing is, you see, the message ID is the same. That's how you correlate the con message with the acknowledgement. The token, the server has to mirror that one, so it must have it in the response, and it's not allowed to modify it in any way, because it's something that the client chooses. Some option, for instance, to tell, okay, the payload is text plain, you have this payload marker, and then you have your response in there. So this message is correlated with the message ID, but the client to actually correlate the request to response uses the token. And well, why you might ask, we already have the message ID, and not only you are or might be confused, there are a lot of people that are confused by this. The reason is there could be something like a separate response. That's basically the opposite to these piggyback, or the alternative to piggyback responses. So we again have a request, encoding, you send it, and then the other side replies with an empty acknowledgement. So it only has the 4-byte base header, same message ID to know, okay, this belongs to this message, and has a code of 0. 0 says, okay, this is an empty thing, and then only sends the acknowledgement. And this results in stopping the retransmissions for this request, but there's no response yet. The advantage of the separate response is you get some time For instance, a small sensor first has to power up some energy consuming sensor, do the reading, maybe even do some processing, and that could take 10 seconds. But if the first retransmission is already after 2 seconds, you would waste energy retransmitting and so on. So you get some time, finally you have your response, and then you can send the response as a confirmable message again. So we use this message type again, but we encode a response code, so we know it's a response. And that's where we need to use this token so that the client knows, okay, this response that came in now belongs to this one request I issued earlier. So that's why it's really 2 layers. You have to separate between the concepts at the message layer. So this is this con, add, non, and so on. And you use the message ID there. And at the request response layer, at this one, you use the token to correlate the different messages. And yeah, if you get the con message, the client also has to send an empty acknowledgement to stop the server from retransmitting, or yeah, say, I got it, it's all fine. There's also something strange cases that could happen with this concept. So you send your con request, and the acknowledgements gets lost. But before you retransmit, you receive this response, and yeah, somehow you know, okay, I got the response for this request. The message itself was not acknowledged, but I know that it has been done. So this is called an implicit acknowledgement, and it's actually, you don't have to do it, but it's quite efficient if you do it, that you stop your retransmissions if you receive this implicit acknowledgement. So stop retransmissions if you know, okay, the request has been answered with a response, and then, yeah, it's a separate response again, so it's a con, and you need to send this ACK. If that's, for some reason, you have an implementation that's so constrained, you cannot take care of this, it's no problem, you can send these retransmissions, that's why we have this deduplication in there. So it's no problem if this happens. This is just, yeah, it's recommended to do this, it's more efficient. And something, I told you there's also this non-type of message, so to do best effort. Just, you know, you can also mix those. So you could send a request on a non-message and hope for the best. The server receives it, but the server is programmed to always use confirmables. The implementation only has confirmables, for instance, because you really want to squeeze something in. You can mix those, and you still have request-response pair. The point is here, you have to be ready for this, that if you send a non-request, you may not expect that our response will also be in a non-message. You must be prepared for cons, and you have to answer with X as well. Okay, there's actually a 4th type of messages, because another thing that could happen is you send your request, it's acknowledged, and then the server is waiting on the actual response. The problem is power outage again. So your client reboots, forgets everything, doesn't know what's going on, and then suddenly a wild response appears. And yeah, it doesn't know what to do with it, because yeah, it doesn't remember this token, it just booted up. And for that, we have this reset type of message. So we can reject something and stop the confirmation as well. This could be interesting for a mechanism we learn shortly about observe. That's something where we receive multiple responses, and to tell the other side, hey, I don't know what this is, please stop doing this. And then you send this reset type of message. So that's the 4th type. With it here, reset. So these are actually 2 bits. So you can encode 4 different values, and these are the 4 message types we now learn. So confirmables, non-confirmables, acknowledgements that go together with the confirmables, and resets if we have to somehow reset the connection. We don't have connections, but there's some implicit state going on. By the way, if it's a non-message you receive and you have no clue what this is about, it was best effort. You can just drop it and forget about it. You don't have to tell the other side. Okay, I was mentioning it could be that there are some retransmissions going on. For instance, see this example. So you have the sender, maybe the client. It sends a confirmable. The problem is the ACK is lost. Then it retransmits the whole thing. ACK is lost again. So what happens? This message will arrive multiple times at the server. It would be really bad if this is something that creates something or uses a lot of energy. And yeah, something, if the rocket is launched twice, that's really, really bad. So you want to avoid it. You want to have this speed application. And for that, you have to store the sender ID. So that's basically the IP address and the port where it came from, and the message ID. And if you have an entry for this, you just filter these duplicates. The thing is, how long should you keep this state? Because, well, it consumes memory, and that's something you don't have a lot of. So there's some kind of lifetime for these message IDs. So in the draft, there's a lot of math, well, really simple math, but that gives you estimates how long this could be. So at first you have this transmit span with the offsets I told you, and you double it every time. This could be 45 seconds. What also could happen if you, for instance, have a ripple network, as you learned yesterday, it's multi-hop. It could actually take a long time. And then if you think there's also the whole internet in between, or satellite communication, this could pile up. So there's some upper bound of latency you should expect. And from basically experience the IETF has with all the years of working internet, what's going on in TCP, this max latency is defined as 100 seconds. So there's a lot of experience in there and some kind of rule of thumb, and the standard says, okay, 100 seconds, then you should be fine, then after that it will be lost. Another thing that adds, there will be some processing delay, so you have to power up the sensor whatsoever. We assume 2 seconds. 2 seconds is about when we start to retransmit something for the first time. So it should be faster than 2 seconds. Otherwise, we have separate responses, so it really takes longer. And then for the way back, we have another 100 seconds. So this gives you in total this exchange lifetime. So this is an estimation that long this message ID could be active in the network. And yeah, you have to reserve or keep this state for at least this time. Then you will know, okay, every copy or whatever of this message using this message ID will be gone, will have left the network or whatsoever. And then you can free up this memory again. You can relax this time. It's something like 4 minutes, so 245 seconds, I think. You can relax this for these non-messages, because you send a non-message and then it arrives, and then you don't need to care about this message ID, because there's no acknowledgement for that. The response to that will use a different message with a new message ID. It's a bit shorter, but it's still quite some time, so 145 seconds you have to keep that. And if you remember, so then you have IPv6 addresses, you have to store them, maybe you can compress them, but it's quite a lot of bytes you have to reserve for all that. So it's recommendable that you relax this and use idempotent requests. I don't know, I hope you know about this, what this means. It's basically you can execute this request twice, and there will be the same effect. So it's no problem if we don't filter, it just arrives again and we do the same thing. Easiest example is a get. So we want to have a copy. You execute this once, you create a response, you send it, then there's a duplicate, you just do it again, you send it out again, because there won't be a bad result from that. The other thing is the classic example, if you have an ATM, some machine, how you design this thing. So it's not deduct 200 euros from this account and do it again. That would be really bad, and we don't have this property. So that's why you calculate first what's the new balance on the account, and then it's something like set the balance to this thing, and that you can do as often as you want. The result will be the same. And that's an important principle you should use in these kind of constrained devices, constrained networks. It really helps you a lot. So that were the basics about the protocol. So that's basically what HTTP was able to do, and how we built this with CoAP with the new UDP binding to have the same kind of behavior you have with TCP. But I told you there are also features that are specifically for the IoT that we need there. So let's have a look at them. The central one, I already mentioned it, is observing resources. So this is these push notifications you really often want from the server. So basically you have a server, a client, and this server has some kind of resource that might change over time. So first the resource state is orange, then it's blue, and at some point the client is interested in the resource state. It will send a request, a GET request, and it will receive a response, and then it has locally the state of the resource. And what you can do, you can use an observe option. So this is one of these options I was talking about. You can include it in your GET request, and what you receive back is a notification then. Basically, it's a response that also has this observe option. That makes it a notification, and that's actually a promise that the server will keep you informed about the resource state. So whenever the state of the resource changes, you receive a notification and have the new value locally as well. So what this does, it synchronizes the state between the actual resource state and the local copy at the client. There could be message loss again. So if you use non-messages here, non-confirmables, it could be that one is lost. So what does this mean? What will happen then? So what we still have caching actually. So every response tells you, okay, you will be able to use this response for that amount of time. So that's basically encoded in this max age. So the default is about 60 seconds. You could set it to 5 minutes, and for 5 minutes you will be able to use it. Even if you haven't heard from me, you can still use it. Of course, at some time, it will be stale and you cannot use it anymore. But probably there will be a new notification and you have to state again. Of course, you see, there's some kind of gap. So the worst case would be exactly here, your application really needs to know what's the state of this resource, and then you don't have a local value. Then you have to basically send this GET request again to get the current value, and that's basically something like a re-registration. So you would find, and by the way, keep informing me, because the reason could also be that it's not lost, but the server restarted, for instance, and lost the information to whom it should send the notifications. Of course, we can also use con type of message, so this is completely independent, so you can choose whatever is best for your application, and then these notifications are just retransmitted, and then you basically just have a short delay, and there's a higher probability that you always have a current copy of the resource state. So this is not bound to which message you should use. This really depends on your application. So there's some kind of rule of thumb. If you have random events, so that there is something, you send a notification, then maybe for a few hours there's nothing, maybe a doorbell or something. You really want to make sure that this event gets there, or this new state gets there, so you would use the con messages. If it's something like a sensor that is sampled and every few seconds you will send a notification, then it doesn't matter if you use one. Still, it depends on the application. Maybe it's something really critical, but often if one value in a temperature series gets lost, it's not a problem. So for periodic sampling, for instance, the non type of messages are good for these notifications. Any questions so far? Anyone asleep? In the back.
Since you are just talking about observing, don't you think that instead of retransmitting response message. So changing the one request, one response basic exchange model should be better to use other methods for sending notification the other way. Other protocols use request message for sending notification. In this case, we have response message for carrying such notification. Of course, in the client-server model, normally the clients just only receive a response. Probably this is the reason, but probably in machine-to-machine scenario, what we call the client, the observer, would receive some post message, for example.
So you're basically talking about the scenario where you have the sensor being a client and it posts the new state or puts the new state somewhere, right? Something like this.
At the end, in this case, notifications just are carried in response. Why do you think they didn't use request message for notification? This is the reason why this observing mechanism has been specified, is currently being specified in this way with the repetition of messages or response.
Mm-hmm. Okay, so one design choice behind this is it's still a normal GET request, and this observe option is elective. So if you have a really constrained server that doesn't know about observing, it sees, okay, this is a GET request, this guy just wants the current state, and you send a response, and this is some kind of fallback mechanism. So it's very transparent to fall back to polling if your server does support this. So that's why it's built through an option on top of GET, not with an explicit subscribe method, for instance, because then it's not that modular anymore. Then you either you have to do it, and then there's no fallback mechanism. With this, we have a fallback mechanism that is very transparent and it's quite easy to implement. There are some other things. So this old model is actually, you see it in HTTP. Because there are no push notifications, you usually have the sensor modeled as a client that posts something to a website to transmit these changes. The thing is, you always have to program this guy where to send the data, and you have to change it, and in between it's not reachable. It's because you don't have the nice mechanism in HTTP. That's why you mostly use HTTP clients to send events or changes of status. And also, the implementation of the client can be very minimal. So you do not implement HTTP. You just implement 3 lines that you send, and yeah, the server will know how to deal with this. The main problem is you always have to really program this, deploy it, and if there's a change, you're less flexible. With this thing, you have some kind of responsive infrastructure, so you can deploy the sensors there, and then you install a new app for this environment, and it can leverage this infrastructure. So yeah, it's easier to have it in a dynamic way, to have dynamic bindings, and then get this information in this kind of push mechanism style.
So in this case, how is possible for the server to recognize, to retransmit the state when is it lost?
So this is, if you think back, we had these CoAP messages. So if you use this confirmable mode, every notification has to be acknowledged by the client. So actually, to go a bit more into detail, even if you use the non-mode, so you don't care, every once in a while you send a confirmable notification to deal with offense. So because there could be a lot of observers in there, and if you never hear from them, you don't know whether they are still interested, whether they are still there at all. So once in a while you mix in a con notification and wait for the acknowledgement. And if you don't hear it, you retransmit. There was no acknowledgement, so it's a normal mechanism. And when this finally times out, you remove that observer from your list.
Yeah, it's on some of the previous slides, but you mentioned that you can have mixed non-con.
Okay,
well, it was actually way before. I don't think you need the slide. Yeah, yeah, that one. What I wonder is, so if the request is con, may the server actually use con or non? I mean, is it up to the server, or how does this work?
Yeah, so it's no implication that if you send something confirmable, that you want, or you cannot force the server to also use this type. So, I mean, the safe way is to always use con, and only if you know your application can deal with it, then you could do the non version.
In the slide before, maybe 2 slides before, you have con, and then I think it was the very first example, the very first timeline you had, even before this. Yeah, this. You have a con request and then a response which is not con.
Yeah, so this is actually the default one. That's the most efficient one. You just piggyback it on the acknowledgement. So this is 2 messages. The other way, if you want to make sure it's 4 messages that you have to send. So
or you could have 3 messages, right? Request confirmable, response confirmable, and act.
About 3, it's only if something goes wrong. You could have a non-request and then a con act. That's how you. If you mix a non and a
con request, con response, and act.
But that was this thing that only if there's an error. You could optimize this. You can think of this. The problem is then the client will keep sending retransmissions. So this act is actually for the case to tell him, hey, stop retransmitting this, because the request might be it is larger than acknowledgement, and it might use several fragments or frames on the link layer.
Con, you're supposed to send an act. You're not supposed to acknowledge with con.
Yeah, so that's it's really 2 separate concepts. So you should follow or must follow the message principle. So if there's a con, you have to acknowledge it. So this is just something that can happen, and recommendation how to deal with it. But the main thing is really, if you receive a confirmable, you have to acknowledge it. And the default way is the most used way is piggybacking. So put the response directly on this acknowledgement. The thing is, sometimes you cannot do this. If it takes time to calculate the response, you need this time. And then you have this.
And there is no way for you to ask the server to reply using confirmable.
No.
Okay, so if you actually want the data, you just have to transmit the request again if it gets lost.
Yeah. I mean, there are even things, because we have Git application and it's always in there, you can also just send a non-request 3 times to make sure it gets there. That's interesting for what was actually on the next slide, or it's up next on the menu, is group communication. So because it's always unreliable, or there's no reliable group communication, and it's not tackled, or it's a problem, but it's not tackled by CoAP. So you always use nons, but to have a high probability that all members of the group receive it, you can send multiple nons.
If you go back to the previous slide, so now you assume the application needs reliability. The slide before again. The client needs reliability. So it uses a CoAP client and those requests, confirmable requests. Who takes care of retransmitting the request if the response gets lost?
That's completely client-driven. So if this acknowledgement, there's a high probability, but it's not retransmitted. So if this is lost, you will have to start all over with the request again.
But it's not inside CoAP. It's above CoAP, right? So it's up to the application then.
Well, if you use cons, then your CoAP implementation will take care of the retransmission.
No, because you get the act.
Yeah, if this is lost, you will retransmit this con. There could be some higher level things like hitting a pipe in the web browser. If you use a non-request, nothing happens, you will send it again. That's kind of the refresh at 5 kind of more. Then that's application driven. That's where you this again. The thing is, what can happen there, because you
I was initially confused by the lack of an act from the client, but it's only but if the server doesn't care, then
It's an acknowledgement. Yeah, that's that.
Yep.
If the server really wants to make sure, for instance, if it was really expensive to create this response, you want to make sure that would be another reason. So the reason is not time, but it's energy consuming. Then you want to make sure it gets there. Then you would act this and immediately send a con to make sure it gets there, and you reuse the retransmissions instead of recalculating the response.
In the observing mechanism, to match the notifications with the first request, registration request, server and client must store the token for the whole time.
Yeah, so this is request response layer. So there we use token to correlate this. So
notifications are reply responses.
Yeah, for this first request. So all of these notifications have the same token as used here in this. There's also, you are able to cancel a subscription. Then you reuse this token as well. So there will be another request reusing this token, and that's basically the handle for this whole observe state. Okay. So where I was already hinting at, there's also group communication. That's quite interesting for the Internet of Things. You want to control groups of things, like multiple lights in the room. And you can do this because it's based on UDP. So you have IP multicast. Of course, it still depends whether it's implemented in the underlying network. If you use normal Ethernet-based IPv6, it's usually already in there. And yeah, it's a bit different for low-power networks, but it's a transparent mechanism. So you just use a multicast address. So for instance, you have a name for that, and then it will be a multicast IP address that you encode in these CoAP messages, and then you can send it out to a group. So for instance, you can get the status of multiple things. You send one out, it will be replicated, reaches all of the things, and then you get also multiple responses. So one request, multiple responses. That's a pattern we already saw for observe. Or you could control them, so you send a put request to all these lights. You set the color to green, and then they all should switch to green. As I already mentioned, it could happen that not all of them receive this message, and you cannot do confirmables because yeah, it doesn't really solve the problem of reliable multicast. It creates a lot of overhead, and reliable multicast is really a standalone problem, and that's something that shouldn't be actually addressed by CoAP. So at the moment we have group communication using IP multicast, but we always use non-messages to do this. But to increase reliability, you can send the same request with a non-message multiple times with the same message ID, because you have this deduplication. So either it's filtered, or if you do a put with this color, it won't hurt if you set it to the same color again. The question is that arises, so it's a RESTful protocol, we have group communication. What exactly is RESTful group communication? So we have a rough idea, but I cannot really tell you what's the bigger concept behind that. So it's quite interesting, this new mechanism, to have it in a RESTful protocol, and what does this mean on a conceptual level. And another quite important topic for the Internet of Things, so machine-to-machine communication, is resource discovery. So the machines won't start using Google. So maybe you can implement something, but yeah, it's not like that. And for that, CoAP already comes with a few mechanisms that are very helpful to do discovery. So the whole thing is based on web linking. That's an RFC that's out there. It's used in HTTP, and it helps you to point to other resources that are out there in the web. And this is extended to the core link format. So it looks a bit like web linking, but adds a few more elements. And how it looks like is this. So this can be sent around as a media type. So it can be the payload. And it basically is a list of resources with some attributes attached to these resources, so you can reason about them. So this is like a mini semantic information, the metadata for this resource. So for instance, you can give a resource type, so some kind of shortcut that you know what you will be dealing with that. You can give the content type. It's this number, so we also have numbers for the content type. There's a registry to not have these long strings to say application XML plus something or the other way around. And yeah, you can have size information so that the client, for instance, knows beforehand how big his buffer should be to actually be able to receive the largest possible response. And there are these elements that actually come from web linking, like the title attribute, which is some human readable string you can give there, which can also be nice if you have it in all this metadata. So this would be something you get from a well-known resource. So there's also an RFC for that. A lot of services are built on this. In the root you have the dot well-known, and then you can have some resources. For us, it's core, or the working group that's working on core constrained RESTful environments. And then you get basically a sitemap of your device. And you can use group communication also for that. So for instance, in your home net, you do a multicast discovery, you get this resource, and then you see what's there, and you can add filtering, for instance. You want all resources that somehow have the type of a temperature sensor. Then only these will answer, and that's how you can discover new resources you might want to use in your environment. There's also an infrastructure-based method with the resource directories. So that works in that way. You have a device, it boots up, and basically it's a server. It provides resources, but on boot up, it's shortly inclined to register with one of these resource directories. So that's something that must be pre-configured. But that could be done during manufacturing and so on, and there's some mechanism how to bootstrap the whole thing. The thing is, these things register with some directory, and then you have a local list on an unconstrained device, maybe somewhere in the cloud, and then you can browse this or have some machine parsing this information. So
when you describe your different sensor with, for example, saying it's a Celsius value, is it related to technology or something like that?
I'll come to this actually later. So there are some attempts currently in some frameworks. There's something like the IPSO profile from the IPSO Alliance. Oma Lightweight end-to-end tries to build a framework. This is supposed to be some shortcut to a semantic description. The thing is, well, I'll tell you later again, we're at the beginning, so the semantics we use for the web, semantic web, the big ontologies, first describe the whole world, and then you can start doing something with it. It doesn't scale for this. So there's a new movement, a grassroots movement for that, so bottom-up semantics. You start with something, something you can start reasoning about. You can build reasoners for small machines even to understand this. And for that, you can use these attributes. So it's, metadata. It's supposed to be somehow semantic information, and you can link it into a bigger framework, like open link data maybe in the end. But you don't go there and have the full specification you know from the semantic web in there. Any other questions? Okay. And the nice thing is, I already told you, we use UDP, DTLS, and maybe something else. This is about alternative transport. So in the Internet of Things, you also heard about this in the lectures. There might be different technologies for different applications. So one interesting one is SMS. To use SMS to implement this RESTful applications and Internet of Things applications. The nice thing is, in the end, we want to have also URIs to describe the whole thing. So you use a different transport, but still at the application level, you can use the same elements. So URIs to define your resource, and then there will be some gateway you will figure out how to reach this thing. And the point is, if you use SMS, you can be much more energy efficient. So it's easy to be in this basically 2.5G mode, and you're very low power, and you're just waiting for SMS. If you send it, you have the benefit that it's delay tolerant, so the network will basically take care of storing that SMS and forwarding it and deliver it when the remote part will come up. Example is if you have containers that are shipped over the ocean, they won't have connectivity for a long time, but if they are close to the port, they see there's a network, and then, for instance, the SMS get delivered, you have these requests. What it could do then is power up other subsystems to actually get IP connectivity over the cellular networks and then start communicating. So this is something that is used in device management. So there are a lot of these kind of modems. You have them in these payment terminals. Luxury cars basically have a SIM card somewhere in the internal system, so not the one for your navigation system, but the one that actually gets firmware updates for the engine, or that can send emergency notifications if there was a crash. And yeah, this is heavily used there, and they're happy to have something like CoAP that integrates with backend services, but run it over the networks that have proven best for their applications.
And this SMS common text of packet, I mean, it can take multiple SMSs. I mean, one SMS is about 160 characters, but if you put all the text inside, so it will have multiple.
Yeah, exactly. So there's a specific how you encode this for this, so you don't use the text and I don't know to base 64. There's a way described in the current draft how you map this. But then you have these mechanisms exactly that you can use multiple SMS. That's something happening at the SMS level that you can also have larger payloads, for instance.
And you can totally replace the internet network by SMS, or it's only to start?
Yeah, that's it. You cannot replace it because this is not internet, so it's a different transport. It's there's no IP. You cannot do anything else, but you can include this application endpoint with the same abstractions. That's the nice part, and it's a transparent integration to then power up, for instance, the IP system. So it's not replacing IP, but it's an alternative. So that's the point. Alternative transports. If your situation or the application needs it, you can use it there. And because the concepts are the same, so the way you interact with these things and how you address them with URIs, they are the same, and that's the nice part. And security. So I myself, I'm not a security guy. I know it's important, but because it's important, I don't want to do security stuff that probably won't work and is insecure. Just to let you know, so we use DTLS, this datagram transport layer security, and Carsten actually already informed you about the ones we have, this elliptic curve cryptography. So it's very efficient with a shorter key length. You have pretty good security. There are different modes supported by CoAP, so you can have pre-shared secrets. You can use the really full certificates, but there's something new called raw public keys. That's basically the private public key. You only use this, and all the certificate information, you do this out of band. So somehow you know that this public key belongs to this device, and that simplifies the handshake, because if you use TLS currently, it takes a while. You have to send a lot of certificates, even certificate chains around to do all this, and there's an optimization for this. That's basically this raw public key thing. And nice part is there is hardware acceleration for that. So manufacturers start to have crypto engines on the silicon, so you can power them up, do the handshake, do these expensive mechanisms that could take like half a minute or a minute on a microcontroller. To have this really in a reasonable time, to have a time constraint also on this handshake. And you can have buffers that are large enough, for instance, to also do security calculations. And then you power this down once you have the handshake, and then use this session key basically to encrypt the traffic. The expensive part is always the handshake to know, okay, this is really that guy, and now we have a secure channel. And that's something where there's currently a lot of work happening. There's this authentication authorization part, so authorization in constrained environments. And the other thing is DTLS profiles, so to know, okay, what exactly should we take from DTLS. So DTLS, it has this whole universe from transport layer security, so there's so many different cipher suits, you can use so many different algorithms. It's a huge framework, and because it's so huge, you really have to define, okay, what do we pick, what should be implemented that we get it small and onto these small devices. So you need some kind of profile that you know, okay, if it sticks to this profile, I can communicate with this guy in a secure way. So what's the status? CoAP is actually a so-called proposed standard. That's an IETF term, so it's a standard since 2013. And this year, a few months ago, it finally was released as RFC. So now the base specification is out there as a standard. There are some other things in the queue, so observing resources, group communication, and blockwise transfers. They're in different documents, so you see it's very modular. So you start having the base specification, and then you can add new functionality in there in a very modular way, which helps you to keep the whole thing you need for your application small. So those things are next in the queue to also become RFCs. And then we need to look at some other things like the resource directory I was mentioning, that's in a quite early stage, or has some better guidelines how to map HTTP to CoAP or the other way around. So where is it used? I mentioned this OMA Lightweight M2M. That's basically Open Mobile Alliance, so those who do SIM cards and these kind of things, what I had with the SMS example. This is a framework to do device management over CoAP. There's the IPSO Alliance, so they built a framework for consumer electronics and so on to have application profiles and somehow kind of what you know from ZigBee that it has this brand on it. You know, okay, it's this product, it will work in my ecosystem. Another thing is ETSC or 1M2M. That's some huge machine-to-machine communication, and their CoAP is a part of it. So this runs off several protocols, and it's a huge machinery, but they also included CoAP in there. There are some examples. The network operators are really interested in that because CoAP helps to replace the old protocols they are currently using. They go back to the WAP times, so WAP. If someone remembers that, there are a lot of weird things in there you don't need in today's networks. Lighting systems. So there's a project by Stack or Sensinode that LA is working on that to actually have CoAP in their street lighting and so on. And there's some nice products like this Spark.io. So this is a low-power Wi-Fi module that already is connected to some kind of cloud service. And to do the device to cloud communication, it uses CoAP. And Kista already mentioned, so there are many out there, but they don't really tell that they use it. But it's really going on. So I also get a lot of interest from the Eclipse Working Group, for instance. There are a lot of companies interested in using that. And we got the RC already recently, so now is the time that it's really booming and going on. So the second part, I don't know whether we still actually have a time schedule for today after this nice start this morning.
And you can go on and then you can stop for the coffee break.
Okay. Okay. So I was using this term a lot, REST. CoAP is a RESTful protocol. I think it's important to take a step back and to repeat what does this actually mean. So what are the principles? Because this is what you should consider if you build Internet of Things application or Web of Things application, to really use this REST architectural style. CoAP is a protocol that implements it, so it already helps you to do it correctly, but there are some other things you really need to know what REST actually means to get everything right. And it's not a simple concept. It's often rather treated like a religion. So there are some hardliners and some other that, yeah, if it's roughly like this, we are already there. The truth is somewhere in the middle. So we need something that has all the nice things that are in REST. So there's Roy Fielding's dissertation. What he basically did, he looked at the web. What's working here? Why is it working? Why is it so scalable? Why do we have the interoperability and so on? What's behind that? And that's what he basically wrote down in his thesis to analyze this for network software systems. So what is REST? The name stands for representational state transfer, and it's so-called architectural style. So it's basically an architecture for an architecture, very meta. That powers the World Wide Web. So there are all the key elements why the web did evolve like it did are in this architecture style. So basically, it's a set of constraints that you apply to elements you have in your software architecture. So what does this mean? This is somewhat an overview what you have in the web. So you have different elements there are some components. Of course, you have data that you have to send around and share, and then you connect these things with some kind of connectors. And the things you know, like the user agent, that's your web browser, and we have something called an origin server. That's the normal web server. You know, you have intermediaries in between, so you could have a forward proxy, so that's maybe something your university or your employer forces you to use, but they could also be something like a reverse proxy, something that is set up by the guys who have this origin server but want to make it scalable. You connect those with, you will see shortly, this client-server model, and what you send around is representations, and these representations you send around, they belong to resources you have. So the data model is you have resources in these origin servers, and you use representations of this state you have there to send around. You even can have non-web technology in there and use gateways to have that. For instance, you can have your Bluetooth device as some custom implementation to talk to this, and then you have your gateway here that actually implements HTTP from here and hides what's going on back there. So yeah, we have different components, user agents, intermediaries, and origin servers. And for the data, the important part is we structure everything in resources and use representations of these resources to send around. So that's basically how to serialize the data that is in this resource so that the other side can understand it. Okay, what are the constraints we apply to these components you just saw? So this is organized how Roy Fielding organizes it in his thesis. It's a difficult topic because a lot of these things are not linear. It's not just, okay, it's this list and that's it. Some of them refer actually to other items in another constraint, and yeah, you can read the thesis, for instance, also quite often and figure out new stuff every time you read it. The first one is, it's pretty obvious, that's very intuitive. You use client-server to connect the components, and that's basically for separation of concern. So you have the origin servers that provide the data, and then you have the user agents that provide the user interface or the application interface to actually interact with the whole system. And the advantage is you can, they can evolve independently. I mean, this is a pattern you also see in model view controller, for instance. So separation of concern, that's something important, and it's also important for networked systems. The second constraint is statelessness. Okay, what's this about? It's about how we do this request-response pattern between client and server. So it's a bit confusing because REST, the S is even in there, so it's all about state that we transfer from a resource to a client basically. But how we do these requests to get it, this has to be stateless. So the point is that each request must contain all the information to understand the request and to process it without any additional context. And for instance, there are cookies in the web, they're used a lot. They are actually bad, so this violates this constraint actually because you need this context of the cookie to process it. So the idea is it's a bit like if you go to the health agency or whatsoever, you have a form and there's a lot of information on this form and then you have to go back, get another form or whatsoever, then you have to go back. And the advantage is this form contains all the information that is necessary to process this. So it doesn't matter to which agent you go, they all can help you and can process this request. So this is very good for scalability. So if you have a server and you want to use multi-threading, for instance, to do the processing or handling of requests in parallel, it helps you because you just need this request and you give it to another thread, or even you have a load balancer, you give it to a different machine, and it has all the information to help you. Other benefits are the visibility. So if you look at the traffic and want to figure out what's going on or why something is not going on, you have all the information there. You know what's going on, and that also helps then reliability because there's not maybe some other context that's stored and maybe lost. So it's it gives you a lot of benefits. So that's statelessness. It's about how you communicate. There's still a lot of state going on because that's what we are sending around. To make this a bit clearer, maybe you can think of the general application that is running as a finite state machine. So in the browser, for instance, you have some kind of states, and you have transitions between those states of finite state machine, and in which state you currently are. That's the session or client state. That's the one that should be independent from these requests. So the servers, they don't care about this. They just receive a request. For instance, if you change from this state to this state, you will send a request, get a response back, and it doesn't matter. So the server doesn't care where you have been. It just cares about this request and to answer this request. There is a lot of connected state going on at the server side. That's the so-called resource state. That's what you store in these resources. But that's really independent from what's going on at the client. Think about just Wikipedia. So you go on, I don't know, a topic you were interested in on Wikipedia, then you find a link about something connected. You go there, you send a request, you get the new page. Then you read that, and then there are two topics you're interested in. You decide to follow this link. Now you're in this state. And there's something in the browser like the back button. You can click the back button, then you're here again. And then you can just send another request and you end up here. The Wikipedia server doesn't care about this. It just gives you the new information, and it can do it very efficiently because of this. Because it's not only you that is browsing Wikipedia, there are many people doing this. And you have many of these requests actually. Wikipedia is mostly read-only. But there are other applications like bank applications and so on. They actually change state on the server. And so I hope you get the idea how this is. So this could also be your bank application. And you click on, what's my account? I want to see some detail maybe. Then I go here and then I want to do some transaction or whatsoever. That's basically the application state. And what's your balance and so on, that's stored in these resources. So next constraint is the cache constraint. So it basically says that responses to requests must have implicit or explicit cache control information. That's basically, I mean, it's pretty straightforward. You want to reuse these responses, so you can have something in the middle that caches this from you, for you, and maybe it's closer, you have a high-speed connection to that. You can just reuse this response from because some other guy requested the same website, for instance, just a minute ago. You don't have to go all the way, I don't know, to Japan to contact the origin server there. So this definitely increases efficiency. So the round trip times are probably shorter to this caching proxy in the middle. It's scalable, so the origin server doesn't really have to answer all the requests that are out there. Some people before can do that, and user perceived performance. So you get your file faster because it's closer to your location. The next one, it's rather big one, the uniform interface constraint. So that's basically how you design an interface for your RESTful web services. So you need to use URIs to identify your data elements, the resources, and you use representation, so representational state transfer, to manipulate these resources. So some state in the resource, and you somehow serialize this into representation. Could be text, maybe it's an image, so you have some abstract data model there, and you can render an image from it, but you can also give a textual representation of it, and that's a representation, that's what you send to the other side. And you don't do these remote procedure calls, so it's not like you call a method and do this. It's really, give me the current account balance, you do the changes to it, and you send the representation of this state back. It's not that for me. You have to model your applications around state that you send around. Another example is we had this observed with the doorbell. So one way you could do this is that you just get an event. So, okay, someone pressed it. Someone pressed it. That's not a good design if you want to have it in a stateful way. So what you would do is, for instance, a timestamp. When was it pressed the last time? Or a counter. How often was it pressed? Then a lot of these other mechanisms like caching work again. And it's about state. So the state is, this is the last time it was pressed. It's not like there was something and it's dependent on how many other things have there been. There's this current state. Representations we send around. And then again we have self-descriptive messages. So we already have that for statelessness, so that all this information is in there. But it's also about the semantics that the other side knows what to do with it, how to process this, and how to get from this representation again to the data model. So if I send something there, it should be in a format that the server understands to actually update the data model behind it. That, for instance, I send a text there, and it can again render an image from that and send it to the next one which wants the image representation. And something more of a detail, I would say, but very important to make it actually work, is that the whole protocol is independent of the transport protocol. That was an issue that the first version of HTTP, for instance, you always had to close the connection when the request was finished. Now you have this keep alive mechanism, so you can somehow encode, this is now a request, now I get a response, and you can keep using the same connection, which gives you advantages because how TCP works. So you have slow start, something like this, and it takes a while until you get the full bandwidth that you actually are able to receive. So make it independent from the transport protocol. That's also an important design choice. And then that's the most complicated part, hate-wise. So what does this mean? It's hypermedia as the engine of application state. So this is connected what we had this picture before. So this is how applications are actually designed and how they're used. So you always have some kind of entry URI, a bookmark. That's where you start. So that's wikipedia.org. That's your starting point. Then you know, okay, there's some search field. You know how to formulate. Let me go back. So you have this entry URI. You do a GET request, and then you get a web page, the initial state basically. And this response, it's hypermedia. That means it's linking to other media, so it gives you links that you can follow. So, and these web links basically give you the choice, which transition to take, or you learn what transitions are actually there in this application. So, you know, there's a link. If I post something to this address where the search form field points to, I can create this request and issue the request and trigger the transition by this. So somehow on the fly I learn what is actually the application space that this application has. Maybe a better example, because browsing Wikipedia is not a striking application, but if this is your banking application again, your browser doesn't know what a banking application is, or what Amazon is, what's the web shop. But on the fly, it learns the logic that Amazon programmed there to order something online. So you start somewhere, Amazon.com, your bank address whatsoever, you get the hypermedia representation that contains links, and those links basically tell you, okay, the next choices in this finite state machine are these. And it also tells you how to issue the request to get to the next state. And that has the thing, it's never hard-coded. So no bank, no Amazon, no Facebook had to program all this in the web browser. The web browser just works. It learns the application on the fly. And this is a very loose coupling between the client and the server. So they can evolve differently. So you change something at the server, for instance, this transition isn't possible anymore, you always have to go there, or you didn't have this state before, it's a new one, you can add it, because whenever you're in this state, the client will learn about this, so it can evolve independently. And that's something very important. It's not something very hard, and it's also one of the most complicated things in this REST architectural style. Did I get my point across? So do you know what I'm talking about here? A question, great.
Could you precisely, what is it for you never hard to code it? For example, you have your HTML code, and it is hard coded, but not in the client, in the page. So all the possible links are listed in HTML code.
Yeah, but you got this HTML from the server.
Yes.
And you didn't know about them before. But the client has to use them to process in the request. The bad approach would be that the client has to know what resources it has to post something to do something for this application. Maybe it comes back to what we had before. If you have this small sensor that posts stuff somewhere, you have to pre-program it there. It's hard-coded in there, and you always have to reprogram the whole thing to do something different. So that's hard-coded. So the other thing would be that, for instance, you write a program to interact with some web service, or I don't know, a watchdog for eBay to do that. The simple way to do it is you hard-code, because you know how this works, what links are there, you hard-code these links, and that gives you the program, so what step after step what to do. But then it's hard-coded, so eBay probably does some optimization, changes this, and now it's broken. Your software doesn't work anymore. If you use this way that you always check, okay, what's there, what are the choices, of course you have to understand them, then you can learn about this. You learn about these updates, and you never have to take care about this watchdog again. Of course, it's very hard. The point I'm coming to this later is, how should the machine reason about this? So that's where it comes back to semantics, to understand it. So let's keep this for later. So that's the actual challenge. But you see, with this example, maybe what I mean with loosely coupled and the bad way to hard code it. It just breaks. If you change one side, it breaks. It doesn't work anymore. And that doesn't work in a humongous distributed system like the web. So if every time Google changes something, all your Android phones or any other service that uses Google services would break, would be really, really bad. And that there's so many patches you have to send around, that does not scale to this level. Any other questions? Good. Let's digest this a bit and move forward. So yeah, this is something where yeah, this came to hypermedia. So that's what you sent around. That what's is linking to other media or other hypermedia. So you have a media type for that, and it basically encodes the representational format. So how this is serialized, how does this contain the data or the data from the model of the application, but it also tells you how to process it. So for text HTML, it's clear this is rendered in the browser, but there are other things that if it's text plain, you know, okay, I can just read this. That's what I do. I have some better examples later. So these are the semantics. So you know the format and how to process it. And as I said, it's easy for HTML because humans can reason. So you just have a textual representation what's behind this link, and then you can, yeah, that's what I want. I want to buy this, or I want to do a withdrawal, or whatsoever. But yeah, for machines, it's really hard to do this. And it really depends on this media type. What do you use? So they're kind of two extremes. So you could use something like application XML. I mean, that was in the beginning, yay, semantic web, and now every machine can understand. JSON is something similar, or text plain. The thing is, it's very useful. So that's the media type you can get out there, and all parties know about it. But concerning the application, it's mostly meaningless. It's just some data. It doesn't tell you how to process it. Then there's something in between. So it's still reusable. This is the ZenML Carsten was talking about. You know, it's JSON encoded, but then you also know this is about sensor markup language. It's something standardized, and you know how to process it. So you know what elements are in there, how to use them. So this is the value for the reading, this is the unit for this value, and so on. And well, the most extreme way would be this: you use some personal media type that exactly tells you, or that's what you hardcode in your client. And that's very meaningful because you know, okay, this is how the actuator control, whatever it is, how this is used. It's in there. That's what you code. And then machines can easily read this. The problem is, yeah, it's very personal, so someone else won't be able to use that. That means you cannot bring those two applications together. So we want actually something reusable, probably as broad as possible, because then if everyone knows about this media type, they can all talk to each other and understand each other. The problem is, if they are meaningless, they are talking about different things and nothing will be done. So we need something in the middle so that machines really know what's going on. So the general rule is, if you design a RESTful application, is reuse media types as far as possible. There's a list out there actually, and you will see it's very, very long, and it already helps you to do this. And if nothing helps you, then standardize something. Don't just do something personal and then you're done. Think about what's behind it, what's exactly missing. Why don't we have this media type, and then put some effort in designing a really good, reusable media type. And then you can internally define it, because you're a big company, for instance, it already makes sense to use it within the company, or even globally. And yeah, there's a procedure how you can actually then register these new kind of media types. That was a big one. So now it's kind of a cut. So the next constraint is layered systems. So we already learned about this. So we saw these intermediaries, so these proxies in there. They're good for caching. You could have load balancers that actually hide that there's a huge compute farm behind that one machine you're talking to. Firewalls you can put in between. Yeah, all these gateways to connect legacy systems. The nice part about this constraint is that you can put them anywhere in your system. And the thing is, it's because one layer cannot look beyond the next one. So if I'm a client I'm talking to this, or I have this URI, I'm talking to this next server. I don't know what's behind that, so how did they implement this? If I go to Google, I can do my search. I have no clue what they implemented to make this actually work. And yeah, that gives you a lot of benefit, because Google then has the flexibility to adapt their system to scale with more and more people using their search and so on. So it's this adaptability, also again scalability, something very important for the web, but also security, because you cannot look beyond it. They could have some very sensitive system there, but they can hide it from you, so you don't see and can do bad stuff. And the last one, so code on demand. It's a bit weird because it's a constraint, it's optional, so it doesn't really constrain you, it gives you something. The point is, it's just something you must consider, or if you consider it, do it like this. So code on demand, the easiest way is tell you that's JavaScript. That's what you download from the server and then is executed inside your browser. The code comes from the other side, but I can execute it locally to add features that haven't been there before, so like animations on websites and these kind of things. So summary, we have these different elements in the distributed system of the web. We have the user agents on one side that kind of drive the application or have the application state and perform something. We have the origin servers. They are mainly used to synchronize, to hold the data that is important for this application. We can put intermediaries somewhere to fulfill different tasks and to scale the whole thing up. And it's all around data. So, but we organize them in resources. We use representations to send this data around, and metadata is also very important to know what this is about. And on these elements, we put these constraints. So we have client-server communication. This communication must be stateless, so that anyone could answer my request. We need caching in there to scale up, to improve the performance. We have these uniform interfaces with this big, difficult one, ETH OS, which comes down to this hypermedia that drives through this application state and actually teaches clients how to use this application. Layered system to put these intermediaries where you need them and be flexible there. And code on demand if you want to improve somehow. And the Internet of Things, it could be some pre-processing. So before you put an updated version somewhere, you do some optimization locally, for instance. That's code on demand. I don't know, how long is it till coffee? Because officially it should be like 5 minutes.
If you wish, we can stop now and have a coffee break and then start again. Or if you want to take some more minutes, it's fine.
Yeah, I think this gives, what I told you right now, it gives you a different angle and it maybe help you to understand it. So maybe finish this and then you have some time to digest all this, or digest, I hope, nice sweets again. So this is something nice, or it's quite famous, how to become RESTful. And this is targeted mostly at people who are aware of object orientation, so how to design applications with this paradigm, or service-oriented architecture, so people who come from SOAP or the WS Star web services. So this is something that if you're a programmer, it's quite intuitive, and how to get from there to what's actually behind REST. So it's called the Richardson Maturity Model. And there is a nice article online, so it was reposted by this Martin Fowler, and basically it tells you, if you start the swamp of POX, so plain old XML, so that's where all these web services for machines basically started. If you have that, what you should do to actually make it RESTful, and what the actual web, why the actual web is so successful. And we have these 3 steps. So first, you introduce resources, you start using the verbs correctly, and then the 3 hypermedia controls That's this big one with 8 UIs. So where started basically these old web services, SOAP and so on, they used HTTP just as a transport protocol or some tunnel to get to the service over the internet. Because port 80, it's always open, it's a safe port. If you ask anyone at the company, the administrator, that port is safe, we can do whatever we want. I think it's bullshit, but that's the situation we live in. So it's easy to reach services and penetrate firewalls and so on. And what they do, they just have a single URI, and then basically they send RPC or use RPC to get there. So remote procedure calls from like object orientation, you call methods there. And the first thing you want to do is you split this single point up into the entities you actually have in your service. So you have multiple URIs to directly address the different entities in your service. So it gives you global addressability, and it removes this thing that it's just a tunnel and then something else happens. So you have a better overview of what's going on. That's step one, but at this point, people still use this RPC style. So they for instance, call some kind of method and have some other method to configure the sensor, for instance. So still this RPC style. So and it's always post. So for instance, web services, the big web services, they always use post to execute some remote procedure. What we want to do is use the verbs. So in our case, the CoAP verbs, and use representations to actually manipulate these resources we find. So these are the central ones. Those are the ones that are defined in CoAP. HTTP has some additional ones, but they are still not really used. And the bad part was until recently the browser actually only used those two. Now we have some more support. And what's the properties of these different verbs? What do they give you? So get gives you actually a contract that whatever you do is safe and idempotent. So safe, you can execute this and there won't be a side effect on the server side. So you won't break anything. You can do this, no worries, and you can do it as often as you want. It will be the same, because if there's no side effect, it's obviously idempotent. Post is kind of the opposite, so it's either safe, no idempotent. So that's something, for instance, you use it to create something new. You post to a bulletin board, and that will create a new entry there. If you post again, it will create the same entry, or the same named entry again, so you have two of them. That's not idempotent. And it's not safe, you don't know whether this actually does something on the server or not. It could be like a method call, so you post a number there, and it will give you the square root or something. That doesn't really have a side effect here. It's safe to do this, but you don't know about this, so there's no contract for that. Then there's put. It's still not safe because you change something, so the intention is to change something, but you can do it as often as you want. Remember that could be good if you want to relax some things in your constraint application. That's the one with the balance. With the ATM, you set it to the new amount and you don't deduct 200 euros every time. And delete, of course, not safe. It should delete something, so they still do how they are called. But once it's deleted, you can try to delete it again. It will still be deleted. And basically, use these verbs as they map to these CRUD operations. So that's a paradigm you can use. So you use post to create something. You can use the request body to have the initial state, for instance. And usually the response body is some action result. So it tells you whether it was successful. Or as I said, it could be something like a temporary state that you put something there, you posted something there, and get the result. So it performs some short-living action, and you get the result. What's interesting, if you create something, there's this location option or location header field for HTTP. It can tell you where this new thing was created. then you created something, you can read it with the get method. That one doesn't have a request body. Technically, you could put a request body, so a payload there, but the server is supposed to ignore it, so don't put it there in the first place. And yeah, the response body then has the representation of what you just read. You can use put to update these things, so if you have a new version, you put it there. The intention is to override what's currently there to set a new value. And then you can basically get, yeah, I updated it, everything is fine, that's what you get back from the server. And maybe after a year you're done, then you can delete this resource again with these things. So structure it with these operations, what you do, how you interact with these resources, and then you're already level 2. The thing is, I hinted at this before with this watchdog, for instance. Often on the web you find exactly this, so they call it a RESTful API and so on, but it's still RESTful, so it's not REST in the full sense, but it's already very helpful because it gets the job done, basically. So what you can do, you have these resources, and then it defines what will happen if you use a specific word there. It will tell you, okay, there's no request, but if you get a response, it will be a JSON object, and you will have these fields, and that's what they mean. And then you, as a developer, can take this value from there and do something with it. The same if you want to change something, it tells you, okay, if you want to change this, do a put request with a JSON, and then they give you the same specification what's going on there. And the problem is this tight coupling, as I said. So if you this is then hard coded in the client. So if the server changed, you also have to change the client because, I don't know, the property was renamed, or more importantly, the path to this resource, it was moved somewhere else, the API changed, then you're tightly coupled. We had this with this watchdog or eBay example. So what's level 3? That's this hypermedia controls. You want to use that, you define a media type for the application, you embed the links there, and that's what drives the application state and makes it loosely coupled. And of course, always you have to exchange some initial URI to know where the service is, but from then you're pretty safe and it will be stable for a long time. And there's a very nice discussion by Royal Feeling where he kind of patched his thesis because he didn't have that much text on this constraint or on this concept of hypermedia as the engine of application state, but it's one of the central ones and it's the one mostly misunderstood. Important thing here is a REST API should spend almost all of its descriptive effort in defining the media types used for representing resources and driving the application state, or in defining extended relation names or hyper media-enabled markups for the existing media types. So what does this mean? I already told you what media types are. They define the semantics, and I told you standardize it if possible or reuse it. So put the effort there, then this is the common language that the applications speak, and they understand each other at the high or at the application level with the semantics behind it. And we want to reuse that because, yeah, that's where the effort goes, and then you can easily build new applications, but you use what is there, and it gives you a bigger ecosystem because more services, more applications can talk to each other. Also, yeah, you have the slides. It's a useful link if you're interested in more details. So, what does this mean for IoT applications? So, let's start small. So, if you have sensors or actuators, it's rather simple actually to model them. So you either have resources that provide you somehow sensor data, so you will read them and that's it. And then maybe there's some that accept a parameter to configure it, or for instance to set or control an actuator to set the target temperature for the thermostat to 22 degrees or whatsoever. And that's rather easy to model because it's mostly dead end, so we don't have this complex state machine where we have multiple states and so on. Basically what we have, we have an entry URI, so we also have that well-known core, And from there, we have this list of resources we have. And then we just go to them, we interact with them, and then we use the back button or whatever, what we do next. For instance, we found, okay, this is the resource to configure this sensor. I do it, I go back, and then I read it. And then usually that's what I do, I keep reading it. So we don't have these complex applications like banking or Amazon. It's quite simple, and that helps us. But let's do this in a correct way. Use these methods. And yeah, we already have a nice set of media types that we can start. So link format, that's the one provided by this resource. It gives you the sitemap, it tells you what you can do. So this first level of links, the choices you can make. Use this, that already helps you. For sensors, this is an interesting thing. Currently it's still a draft, but yeah, we have to learn how to do this in the best way that it's really reusable. So a lot of effort goes in there, that's why it takes long. But that's something really interesting. Use that. Another example, there's this GroupCom document in the co-working group, and it defines a media type to manage these groups. So it's then a really RESTful approach how you manage these groups. So you know this format, it's JSON encoded, but we predefined what the items mean, and we put enough effort in there that we don't have to change them yeah, every year or whatsoever. So put effort there in designing the media types, and then reuse them. And yeah, if you understand this media type, you know how to process it and how to modify it to update the resource state by sending a new representation there. As I said, there are these attributes. They're interesting. They are basically these relation names. So relation names, if you have HTML, you have different links, and you can put this attribute of a relation there. It basically describes you how to follow this link, what you should do, how to create your request. That's represented in these attributes we have in the core link format. And they give you some metadata, how to follow this link, how to create a request. And there are some discussions because you get typed resources. So if you follow this link to the discussion with Roy Fielding, he says it's a bad thing to have typed resources, but it's more what you saw with this RESTful API where you specify everything and then you have to hard code it in your client. That's the bad one. That's the badly typed resource here. It's more about these bottom-up semantics. So and that's what we want to build. So we have to somehow teach the machines to reason about what we encode in this hypermedia, how they can follow these links, and from there we can take it to the next step and then actually build larger RESTful machine-to-machine applications. There's some other mechanisms you can look into. You can do exception handling with the right response codes, so that you, for instance, there's a class to tell, okay, the client did something wrong, or something bad happened on the server. There's something called content negotiation. I have this, so you have some state in the resource, and you can serialize it in different formats. And whatever the client likes best, he can ask for the right serialization or representation it can understand. And there's some other things you can control requests a bit, so put a condition on them. So only create this if it didn't exist before. This is interesting if you have concurrency, so multiple IoT devices interacting with some service, put some conditions on there, but I won't go into detail, but it's really something interesting to look into. That would be that part. Do you have any questions so far? I guess you're hungry, you have a headache, it was too much, I'm sorry. Let's keep the whole day interactive. So you can ask me at the coffee, we will have the hands-on, we can try this out. If you have already experience, we can talk about some details. If you started, I'm happy to rehearse some of the basics. So I hope it's a fruitful day.
Great, thank you very much.